Woohoo! Go Bearcats!
Well, good evening, Bearcats. This is 3.1, exponential functions and their graphs. I want to give you a little bit of history and where we've been and where we're going with functions right now. All right, so far in the text, as stated right here, we've dealt mainly with algebraic functions, which have included polynomials and rational functions. In this particular chapter, we're going to study two types of non-algebraic functions, exponential and logarithmic functions, which, by the way, are inverses of one another, and that's a really important piece of information that's going to help us a little bit later on when we get ready to graph logarithm functions. Anyway, these two functions are examples of what we call transcendental functions. The definition here of exponential functions, and that's what we're going to talk about tonight, is exponentials, is f with a base of a, is denoted by f of x, and it's a to the x power, the base of a to the x power. The power is now actually our variable. So this is where a has to be greater than 0, and it also cannot be 1, because of course 1 to any power would just be 1. 0 to any power is undefined, so we can't have that. It has to be greater than 0, and it cannot be 1. And x is any real number, Things that we should learn is we should learn to recognize, evaluate exponential functions with base a. We're going to do that tonight, and we're going to talk about graphing exponential functions and using the one-to-one property. Those are the two things we're going to go on tonight. Later on, we'll learn about evaluating graphs of exponential functions with base e, and we'll also learn about exponential functions modeling real-life problems. All right, let's move on to our next piece of information. Let's talk a little bit about the graphs of exponential functions, what they look like, the shape of them, and what they have in common. Notice something, that all the graphs of exponential functions have similar characteristics. Here is the base graphs of y equals a to the x power. Y equals a to the x power. I'm going to take two functions here, 2 to the x power and 4 to the x power. These are two exponential functions with different bases. I'm going to go ahead and create a t-table over here for the first one. So if we were to create a t-table of the values, you would simply plug in values for your exponential functions. So if I were to plug in, let's use -2, -1, 0, 1, and 2 as my x values. If I plug in a -2, I would get 2 to the -2 power, which you would rewrite, hopefully you remember, as 1 over 2 to the +2 power, which you would rewrite as 1/4. So 2 to the -2 power would be +1/4. 2 to the -1 power would be +1/2. Anything to the 0 power is always 1. Of course, 2 to the first would be 2, and 2 to the second would be 4. And that would be our t-table of values, and that's sort of what we've got here. So notice that this lower equation, this one that's a little bit lower, closer to the x-axis, is our 2 to the x power. Notice again, we had at 1, we were going to be at 2. At 1, we're at 2. At 2, we're at 4. At 0, we're at 1. At -1, we were at 1/2, etc. So this is actually also moving upward on the right, so it's like a growth function. All right, next we're going to talk about the graph of y equals a to the -x. Again, we have 2 to the -x and 4 to the -x. Two different bases, and we've taken the x values. Notice that the x has the negative. In the past with transformations, it meant that we reflected, and if we were reflecting x values, they would have moved horizontally, and we reflect over the y axis. That's really what has happened here if you look at these two from a transformational standpoint. I also want to create a t-table for this, though, algebraically, how we would figure that out. Again, I'll use the values -2, -1, 0, 1, and 2. And let's take a little algebra lesson down here. So we have 2 to the -2, which makes it 2 to the +2, which makes it 4. And if you do 2 to the -x and it's a -1, that cancels out and you'd be a +1, and that would be 2. Of course, anything to the 0 power is 1. 1 to the negative 1 would again be 1 over 2 to the positive 1, which would be 1/2, and then 1 to the negative 2 would be 1 over positive 2, which would be 1/4. All right, so that's how we compare them. And again, if you take a look at this graph right down here and our ordered pairs, we would have at 2, you're at 1/4, at 1, you're at 1/2, at 0, of course, you're back at 1. Notice something important. All the base graphs of exponential functions all have the ordered pair from a base function at 0, 1. You're going to learn later on that all logarithms, base logarithms, have the ordered pair 1, 0 because they're inverses of one another. Now, if this graph shifts left or right or up or down, of course, that value would change. But from a base graph, that's what it would have. All right, you're also at -1, 2, and at -2, 4. And that's something that our graphs look like and what they have in common, just to get you back familiar. You did do this in Algebra 2, but just to get you a little familiar with it again. All right, let's learn a little bit more about our graphs. Some characteristics of our graphs. Notice that this is an exponential growth graph. We're moving up. The other, when it moved down to the right, was an exponential decay graph. It was decreasing as it moved to the right. The domain value, the x values, of course, are all real numbers for regardless if it's growth or decay. The range in both cases is from 0 to positive infinity, making the x-axis in the base functions a horizontal asymptote. So notice that. The y-intercept is 0, 1 in both cases, and that's true for all your exponential bases. This graph is increasing while this graph is decreasing. This is actually called growth when we get to applications, and this is decay when we get to applications. That comes into play a lot, especially with base E. Right now we have base A, and we will have eventually some base E questions. They're both continuous graphs. There's no break in your graph. All right, let's take a look at this little statement over here on this side. This is all about our one-to-one property, and we're going to work a lot of your problems in class today have to do with one-to-one property. Notice in the two figures on the left that you can see the graph of an exponential function is always increasing or always decreasing. As a result, the graph passes the horizontal line test. Therefore, the functions are one-to-one functions. We can use the following one-to-one property to solve simple exponential equations. So look here. For a being greater than 0 and a not equal to 1, which is true for all our exponentials, then you have that a to the x equals a to the y if and only if x is equivalent to y. The bases would have to be the same. And then the two at the top, the exponents would be equal to one another. Let's use this property in a couple of examples. Here's our first example. We have 9 equals base 9, and basically that'd be base 9 to the first equals base 3 to the x plus 1. I'm going to rewrite 9 with a base 3. I could rewrite 9 as 3 to the second power. That's the same as 9, so I'm replacing 9 with base 3. And then I could say it's equal to base 3, x plus 1. The bases are now equal to one another. Therefore, we're going to solve by setting the exponents equal. So the bases are the same, so now we can say 2 equals x plus 1. We would subtract 1, and we would, of course, have x is equal to 1. X is equal to 1. If we plug that back in to check, that's a pretty easy check. We could say 9 equals 3, and it would be 1 plus 1, which is 2. 3 squared is 9 equals 9. I believe we've got a winner. All right, next example. A little trickier with the fraction over here. Remember, we can change these to base 2. So I could make this 1 over 8, so they're both fractions, or I could move the 2 up. I think that's really preference. I really don't like to deal with the fractions, so I'm going to move my 2 up. And when I move my 2 up, if you remember that property, it's going to change my exponent to a negative. So I'm going to have 2 to the negative x power equals. I'm going to rewrite 8 as a base 2. 2 to the third power would be equivalent to 8. Now my bases are, now my bases are the same. So I have a 1-to-1 base. So now I'm going to set my exponents the same. So now I'm really dealing with negative x equal to 3. Therefore, x is equal to negative 3. All right, that's really it for tonight. It was pretty short and simple. Your classwork is pretty short and simple tomorrow, and then I'll go over any review questions you might have, and we'll just go on our merry way. Hope you have a great night, and go Bearcats!